Next up, we have a ball oscillating on a simple pendulum, and we have been given the period, and we're saying that the pendulum is now taken to the moon, where G is half as big. So you could do this with numbers, so you can actually just plug in a number for G that's half as big as it is on Earth. Or you can do this in the kind of factor style question that we've done before. I'll do it the second way. So the period of a pendulum on planet X is going to be 2 pi times the square root of L over, that's not G, over whatever the gravity is on planet X. And the problem tells us that this number here is half as big as it is on Earth. So that is 2 pi times the square root of L times whatever it was on Earth divided by 2. And now the question is, we know that on Earth, this is 2 pi square root of L over GE. So we'd like to make this look like that, which means that we're going to have to pull out that 2, which is in the bottom of the thing in the denominator, in order to get that to look like that, and we'll be able to compare the two. So think of this as being 1 over 1/2. 1 over 1/2 is 2. So that is going to look something like that. The 2 bumps up to the top and looks like that. And now it's pretty straightforward to see that that 2 can just pull straight out of the square root. Square root of 2 times 2 pi L over G of Earth. So that is that, and we have that the period on planet X is square root of 2 times whatever it was on Earth. So on Earth, it was 2. So on planet X, it will be square root of 2 times that. So square root of 2 times 2 is 2.8. So 2.8 seconds. If you don't like working in symbols here, you could make up an L and plug in 4.9 for that and figure out exactly what the period is on Earth, and you should get 2.8 seconds, and it would work just fine. In order to do that, I shouldn't have said it that way, actually. If you want to do that, what I just said won't work, because you can't just plug in any L. So if you want to make this be 2 seconds, then you need to plug in 2 seconds for that and 9.8 meters per second for the gravity on Earth, and solve for what the actual length of this pendulum is. Once you get that length, you can plug it into there, and you'll have an L there and a 4.9 there, and then you should get 2.8 seconds. Next is which will increase the frequency of the lowest frequency standing sound wave on a stretched spring. I like doing there could be more than one correct choice on review sheets, but I don't put them on tests. So all test questions in the lecture class will only have one answer. This is a good way to get you to think about a whole bunch of different ways, and think about why different things are wrong. So if we replace the string with a dense string, if you played a stringed instrument, then this one is kind of intuitive to you. And you know that the thick strings are the ones that make the low notes. But if you don't, that is fine too, because there's an equation for that, which says that if you replace the thing, you have that the speed of that wave depends on the tension in the spring. So the F sub T divided by the mass density. So a thicker string is going to make that get a bigger mass density. So we've increased the number in the denominator here. So we've made the speed of that wave be smaller. Now we can think about frequency as being speed over wavelength. So we have that we have that the speed of the wave is lambda times f. So the frequency of that wave is v over wavelength. If we're not changing anything about the length of the string, then that's going to stay the same. But we just rationalize that the speed has to go down. So the speed of the wave is going down, which means that the frequency has to go down. So this will lower it. So that's a no. Increase the tension in the string. By the same logic, we can look at this equation. So we have that V is the tension divided by the mass density. Now, if we make that number bigger, we'll make that number bigger. And so this is going to do the opposite of what part A did. So now we have frequency is still V over wavelength. Wavelength is still the same, but now V has gone up, so F has to go up. So that will definitely get her done. Plucking the string harder, that is akin to changing the amplitude of the displacement. Nowhere in the equations is the amplitude have anything to do with the frequency. If you pluck the string harder, you'll initialize a different set of harmonics, and it will sound a little different, but that is not gonna change anything about the frequency of the thing. If you double the length of the string, let's return to this here. So frequency is V over wavelength. Doubling the length of the string is not going to affect the speed of that wave, right? The speed of the wave is determined by the tension and the mass density, but that will affect the frequency of the standing wave that you oscillate. For a wave on a string, the lowest mode of oscillation looks like that. And so the wavelength here is going to be twice that length. So if we make this longer, then we have effectively increased the wavelength of the wave that you oscillate. If that doesn't kind of physically just make sense to you, there's also an equation for that. On your equation sheet, there's an equation that says that the wavelength of the mode that's oscillated is twice the length 2L. So if we make L bigger, we also make wavelength bigger. Either way, the wavelength of the lowest frequency mode on a string and all of the other harmonics has gone up. So frequency has gone down. That will also lower it. Frequency will be lowered for D, and the only answer there is B.